To start, I'd like for you to try to empty your mind of all your preconceived notions about solar energy, all the things you've learned about solar energy, because they don't apply to this technology. I want you to start with a fresh mind. What you see here are two applications of our technology. What you'll find out in a few minutes is that the illustration on the right is an individual module, and the illustration on the left is the deployment of quite a number of those modules. So the analogy you might begin drawing here is that this is like a wind machine in that respect. That is, that every single module is identical to every single other, so they're not individually customized and engineered each time you deploy it, and all the components, or almost all of them, are made in a factory, rather than being a big custom engineering project like most concentrated solar power is. So to start, I'll just give you a little background on the company, but first a little bit more about my background. I actually got started in solar energy when I did my master's thesis at MIT in 1973. And I've written a number of books on this subject, testified to Congress, was on the advisory board of the National Renewable Energy Laboratory in the United States, and as was mentioned, on the board of trustees of MIT. The company has its origins at MIT. It's a spinoff. The technology was developed with funding from the U.S. Department of Energy. And we were very fortunate to have very, very capable technology development partners as part of our team. And you can see this list up here without my reading it for you. So this is one of my favorite quotes from one of my favorite faculty members, one of my professors, a well-known gentleman, Don Sadoway. And I'm going to show you that part of our system is indeed made from dirt. In fact, it's our thermal energy storage system. So this breakthrough in solar energy is based on these four elements. First is the world's most versatile and reliable power generator. You're all familiar with microturbines, I'm sure. And by the way, some of you will find the level of technology may be too simplistic, and others may find it more complicated, but I'm trying to draw a middle line. So I'm going to assume that you know, in this case, what microturbines are. And I'll be talking more about microturbines in a few minutes. And then we add to it the world's largest, highest temperature air heating solar receiver, up to 970 degrees centigrade, which is the highest operating temperature of any concentrated solar power systems, which usually tap out at about 600. And as we all know, higher the temperatures, the higher the efficiency. Then, of course, we use as low-cost heliostats as possible, the reflecting mirrors that track the sun and reflect the light on top of a tower. And we couple that with the cheapest possible thermal energy storage. We know that storing heat is far cheaper than storing electricity. In fact, even molten salts is only about 10% the cost of batteries, and this is less than half the cost of molten salts. So, and I'll talk more about each of these elements in a few minutes. But in addition, this approach offers grid operators characteristics they've never had in any kind of power generator. The first one is this is clean energy, low emissions base load. As far as we know, there's no other approach to base load clean power that operates 24/7. Couple that with grid stabilizing. Unlike PV and wind, which destabilize the grid, this actually stabilizes, and I'll explain more about why that is in a few minutes. And of course, even coal plants destabilize the grid. If they go out, and you're down, 500 megawatts or something at a crack. It's also distributed. And it's a technology that's not centralized. All CSP generally is centralized, and this is a distributed form of CSP. And that has benefits and reduced costs of distribution and transmission. And finally, it's literally 100% reliable. What do I mean by that? As you'll see, and I showed you in the very first slide, when you deploy many of these in the same location, if one of them happened to have a maintenance problem and is down, you still have many, many more that are still operating. And these microturbines have uptimes of over 99%. So each unit itself is highly reliable. And another thing about what that means is that when you deploy one of these power plants, you don't need a backup power plant someplace else. So you only have to build one plant, not two. So this is our target, coal competitive clean energy. This is very important if we're to address the challenges of climate change, which, as we all, I think, agree, is not a trivial challenge. We all must do, every single one of us must do everything we possibly can to reduce that pending challenge to all of society. So, as I said, origins out of MIT, funded by the US Department of Energy. It's competitive with PV if you're trying to get 24/7 operation out of PV. And remember, we're at the top of our cost curve. PV is near its bottom. It's not there yet, but it's near its bottom. We're starting off at the top of our cost curve. And for power project developers, this is offering attractive returns. So we hope this is attractive all the way around. So this is a single module. This is the only solar system that has a name, a brand name. You think about that. You can have solar panels, and you might be able to say, well, those are somebody, XYZ solar panels. But the whole system itself, it does not have a branded name. CSP system's the same thing. You can say, well, that CSP system is done by BrightSource, but it's not a branded product. And by productizing CSP, we get the costs down. So we call this a 24/7 solar plant. The initial system is 333 kilowatts, which is based on the initial microturbine that we're going to be using from Flex Energy. So that's determined by the size. That's what determines the size. And this whole system has so few moving parts. So few moving parts. It's very simple to operate. Very low maintenance. You don't need anybody on site to operate it. Sort of like PV plants in that respect, but very unlike Rankine cycle steam turbine plants. It uses air. Now this is a CSP system that does not use water, steam. It does not use molten salts, and it does not use heat transfer fluids. Just air. And the air is at ambient pressures, not high pressures. So there's sort of one layer of simplicity on top of another here with this system. So these are the 5 subsystems. I'll start off here at the bottom left, off-the-shelf, proven, tracking heliostats that reflect the light up on top of the tower, to the solar receiver that I've already mentioned that heats air, no moving parts. It's an upscaled version of a proven receiver that the German Aerospace Center, DLR, developed many years ago, but that operates at between 4 and 11 atmospheres. Very competent. I'm going to show you that in a few minutes. And then number 3 is a tower, not shown, but what is shown is the air ducts that go up and down. And the way this operates is that the cooler air from the storage, which I'll mention in a minute, and the power block down here, the microturbine, that the cooler air goes up, is heated by the solar receiver, comes down, some of it goes to the storage, and some of it goes down to power the turbine. This is all during the day, and I'll show you some system diagrams in a minute. And then, of course, the microturbine, but we've modified it a bit so that it efficiently uses solar heat. And then number 5, the thermal energy storage system, which again I'll talk about in a few minutes. No moving parts, 100-plus-year-old proven technology. So very little risk associated with this system. So as I said, developed with funding from the U.S. Department of Energy, a series of 2 phases. The first phase was a very thorough engineering and cost study, $1.5 million effort over the course of a full year to identify the performance and the cost and so on. I'll talk more about those things in a few minutes. And then finally, the second phase was to develop the breakthrough changing technologies here. These are our key partners. And without dwelling too much time on this, you can see the names. Most of these I know are familiar to you. And each of them played a very vital role in its development. So here's the system breakthrough, and this is what you might be most interested in. You know, why is this new? Well, first of all, Brayton Power Towers is not a new idea. That's been around for a long, long time. The problem with this approach in the past has been is that it's been a high-pressure system. And what that means is that the air from the compressor was diverted and goes through the solar receiver and then back to the turbine to power the turbine. The problem with that approach is that now the solar receiver is also a pressure vessel. In fact, the entire system is a pressure vessel, which is a big challenge when you've got such a huge system with ducting and blowers and everything else. And as you'll see in a second, when I show you the receiver, it's a very small system, only 100 kilowatts, and only when the sun is shining. So we turned it into a low-pressure system. And the way we did that was by introducing a high-temperature heat exchanger that was invented by a professor at MIT. And when I show you the system configuration, I'll show you where we put that so you can sort of figure out how this thing all works. But as a result of the solar receiver now being at ambient pressures instead of high pressures, the initial system, the receiver of our system produces 7 times more heat than the high pressure receiver. So that enables us to not only power a 333 kilowatt turbine during the day, instead of only 100 kilowatts with the high pressure system, but also allows us to store about 13 hours of heat at night. And that's a variable number which, for those of you who are really experts in CSP, you understand how that's a variable number. So here's the system diagram for daytime operation. You'll see how simple this is. So the cooler exhaust air from the storage and from the power block are blown up to the receiver. The lights from the heliostats here. The air comes out at 970, and 1.7 of the 2.7 mass flow goes to the storage. So we're actually storing more heat during the day than we're using. And the rest of it goes down to power the power block during the day. So that's the daytime. At night, some of these dampers, there are only 4 dampers, very simple. And those are the primary moving parts, of course, along with the blower. So that's closed, and now the exhaust from the power block goes in a reverse direction through the thermal energy storage system, comes back down, and powers the turbine. Now we also have a fuel-only version, but before I show you the fuel-only version, I'm going to show you where we inserted the high-temperature heat exchanger. As we all know, microturbines have their own recuperator built in as part of the system in order to increase the efficiency from 15 or 18% to as high as 33%, which is the ISO rated efficiency of this particular turbine. We inserted a high temperature heat exchanger right here. So the compressed air goes through the recuperator, the regular recuperator, and then goes through this high temperature heat exchanger, and then from there it goes to the turbine. Okay? Here, we inserted a inline combustor that can burn either a gaseous or liquid fuel, that if the air coming off the solar receiver or coming out of the storage is not adequate and you want full power, then you can add a little fuel to raise the temperature and get full power. Or in weather like we've had the last couple days here, that is cloudy weather, no CSP output, you can burn fuel all the time if you want full power, if the off-taker wants full power. And that's a choice, of course, that can be made as part of the control system. It's not required, it's a choice. So I'm not going to go through this, but in more detail are the mass flows, so 6.5 kilograms a second at maximum. Of course, atmospheric pressure throughout the whole system, and we have the various temperatures at various points along the system. Here's the DLR high pressure receiver. The way this works is rather simple, although ultimately this air heating solar receiver is a bit complicated, and I'll explain why. The way it works is that the cooler inlet air comes in, goes around the entire perimeter, comes through this cavity here, so it's called a volumetric receiver, and then that air comes through this solar absorber, which is a silicon carbide foam. An enormous amount of surface area, not only to capture the sun's energy, but also to transfer that heat to the air. So it's an extremely good heat exchanger. Right here is the window that has two functions. It lets the light in, of course, but when this is a pressure vessel, it also has to keep the high pressure inside. Now this is what makes it a pressure vessel. And because it's a pressure vessel, that window can only be about 60 centimeters in diameter, very small. And that's why it can only power 100 kilowatts. Our solar receiver, you can see how the DLR is the primary co-developer of this. They helped us develop this. It's an upscaled version of theirs. So in a very similar manner, the cooler air comes in around the entire perimeter, is drawn through what we call the inlet absorber, which is an in-canal mesh, and then goes through that same kind of absorber and out the back at 970. This window here is not under pressure. So instead of being 60 centimeters, it's 2 meters. And that's why it puts out 7 times more energy than the high pressure. What I did not mention that makes this even more problematic is that this has 3 active cooling systems to keep it from falling apart. The most important is the frame around the glass, because you get differential temperatures in a receiver like this. And if the frame has differential temperatures and thermal gradients, it's going to have a lot of stress. And so it's very likely to break the glass. And that's the end of it. It also has this secondary concentrator here to make the aperture effectively larger. This is reflective, but this also has an active cooling system, a liquid cooling system to keep it cool. And finally, it has blowers to keep this glass cool and keep it from melting. So lots of problems, and you have to keep it from melting because it's so close to the absorber. As you can see here, our glass here is quite a distance from the absorber by comparison. So we have no active moving parts. There are no moving parts in our solar receiver. So now storage. Many of you are, perhaps even most of you, are familiar with Culper stoves or hot stoves that are used in the steel refining business. So it's technology that's been around for more than 100 years. And these are big brick containers filled with fire brick or checker blocks, and they operate as high as 1,500 degrees C. Well, this is a scaled down version of that same technology. So it's less than 10% the cost of battery storage, probably more like 5%, even with declining costs of batteries. It's relatively modest size, 3 to 4 meters in diameter, 9 to 7 to 9 meters tall, filled with fire brick or checker brick, space for airflow. And here's an example of checker brick down here in the corner. You can see how these things are designed to be quickly stacked, and they have holes in them through which the air passes. It operates, of course, at 970 at ambient pressure, atmospheric pressure, no moving parts. So these copper hot stoves have unlimited cycles, unlimited, unlike a battery. And also unlike a battery, it has more than a 95% round-trip efficiency. The efficiency depends entirely on the heat loss, and the heat loss depends entirely on the engineering and the use of insulation. So again, I think most of you are familiar with Brayton cycle microturbines. The reason we call these the most versatile turbines in the world, well, number one, they're plug and play. When these are shipped from the factory, they have all the power electronics required to connect to the grid. No inverters, nothing else is required. So they're shipped to the site, you put them on a pad, like a gravel pad, connect them to the grid, connect them to a source of fuel, and they're ready to operate, more or less. And they can be powered, of course, by solar, minimal fuel backup, and if so, it could be biofuels or diesel, any liquid or gas fuel. Firmly dispatchable, simple. These have a 99% uptime, but more importantly, on an annual basis, they require only between 4 and 8 hours of routine maintenance. And they have MTBFs of around 100,000 hours. These are amazing machines. And finally, as I said, they're grid stabilizing. They are so nimble in their operation because they're very small. You know, the turbines are only about this big in diameter, unlike steam turbines, which are huge. So these adjust very, very rapidly to fluctuating voltage and demand on the grid. They can operate at full power down to half power, and even at half power, they're about 80% of their rated capacity. So microturbines really are pretty amazing. And there's a nice article that explains more about the advantages of microturbines. So here's how we did the LCOE analysis in our studies with the Department of Energy. The DLR modeled the productivity of the system on an annual basis. We determined the component costs and the site and balance of plant. We used vendor estimates, bill of material estimates, public information, and the entire team worked on that. We extrapolated the cost to 2 gigawatts of cumulative deployment, which at the time seemed like a lot, but the rate at which solar is being deployed around the world, 2 gigawatts, is really nothing in the scheme of things. And we used a tried and true cost learning curve analysis, and we assumed only a 10% cost reduction for each doubling of cumulative factory production, 5% for commodities. And that averages out to about 7%, which is about half the decline in cost of PV, which is declining about 15% with each doubling of cumulative production. We determined O&M costs using published and anticipated MTBFs and so on. This was done by Worley Parsons. We extrapolated those also to 2 gigawatts, and Worley Parsons ran NREL SAM model to determine the LCOEs. The CapEx, we compared 3 principal systems: our low pressure system, a high pressure system using 7 of DLR's high pressure receivers, and then we compared it to a 1700 kilowatt turbine that's on the market, also a low pressure system. And without going into all the details here, the lowest cost, as you might expect, is the 1700 kilowatt system. And we've determined that our one reason we did this is because we knew that from the design of our solar receiver that it would be a fairly straightforward engineering matter to go from 333 kilowatts up to 1700 kilowatts. But the reason we didn't go there initially is that just going from 100 in a high pressure receiver to 333 with a low pressure and increasing the output by 7 times is already a big step in scaling up technology. So we were trying to manage technology risks. But what I can say is that we are highly likely to have these larger systems within 2 or 3 years. And the analogy here again is to wind machines. I think most of you in this room can remember when wind machines were only a few hundred kilowatts, and now they're several megawatts and still growing larger. Here's the productivity analysis by DLR. DLR has all the tools. They're very well refined and very well accepted and understood tools in doing the modeling for these kinds of systems. And the capacity factor for this particular design, which is not the only design, we expect to get larger capacity factors in our commercial designs, ranges from 60% to 66%, most of that from solar. And part of those, what we consider low capacity factor numbers, we think we'll get closer to 80%, was determined by the requirements that DOE placed on us in engineering the initial system. And DOE also put constraints on us with respect to certain assumptions that go into the SAM model. For example, here's one right here. The debt equity ratio is 50%. Nobody builds power plants today at a debt equity ratio of 50%. Typically the debt is as much as 80%, and sometimes even higher depending on the technology. And of course the return on debt is much lower than the return on equity, and so we were penalized in that fashion too. And there are a number of other ways in which we were penalized by the requirements that DOE posed on us. And these are some other assumptions. It was a long list of assumptions. They include the contingency, the EPC, and so on and so forth. And because they were assuming that this is a conventional technology, and whereas ours will be assembled very quickly on the site, and those costs will be lower. So using those assumptions, our initial costs, these are all US costs, not Sri Lankan costs, not China costs, just the all US costs. Initially, assuming 100 megawatts, assuming a 100 megawatt project, the LCOEs would be between 11 and 12%, and after 2 gigawatts, they start dropping below 8%. The 1700 system is 2 cents lower at each point along the way. And so we have a system that we know is going to be able to go to 6 cents or lower. And again, that's with that high debt equity ratio, high interest rates, and so on. So what about risk? Well, as I've stressed a few times, mostly off-the-shelf equipment. You've got the microturbines, the solar thermal storage system, 100-year-old proven technology, solar receivers, scaled up with simplified proven, heliostats are off the shelf, and a conventional tower, conventional air transport system. So the really key here is the systems engineering, and that's underway as we speak. So we also have a roadmap for continuing to drive up the performance and drive down the cost. Like I already mentioned, the larger power sizes, reduction of 2 cents. The professor at MIT who invented the high temperature heat exchanger invented a ceramic turbine which will have between a 40 and 50% fuel to power efficiency. And any increase in the efficiency of a CSP system has a significant impact on the CapEx. And then finally, there are a range of things like using phase change heat storage materials instead of brick. Those materials might be more expensive, but they're lighter weight and smaller and more compact, and they can be on top of a tower instead of on the ground, as brick must be. That would save money in a variety of ways. Also, we can use, as you know, there's considerable waste heat, useful waste heat, over 300 degrees centigrade coming off these turbines. Very useful for industrial processes. But if there was a modular water purification or desalination system, that would be ideal. And then, high efficiency coatings for reducing, for example, the emissivity of the absorber. Now I'm going to compare our technology to others. So the first generation technology, I think you all know about about power towers, very large projects, parabolic troughs. Parabolic troughs are the oldest, and they got a jump start on power towers. Power towers are starting to overtake parabolic troughs in terms of market penetration. And finally, linear Fresnel systems, which are kind of stalled in the marketplace. I still like them, but they don't seem to be being adopted very quickly. All of these, of course, are Rankine cycle turbine systems. And more or less, they're customized for each situation. So here's how we compare to these systems. I'm not going to go through each and every line here, because that's not the point. The point of this is the color. We compare ourselves, just take, for example, reliability. You have conventional reliability in conventional CSP plants. But I already described earlier how our reliability is super high. And I described that there are two reasons for that. But I won't go into that. But I could do this at each level here, at each characteristic. And the same is true as I compare our system to PV and wind and building new conventional power plants. As you can see, our characteristics are better each step along the way. We have to be the same, more or less, with O&M as PV and wind. But one of the points I'd really like to make here is if we lived in a world of clean energy, particularly wind and PV and CSP, and somebody had this bright new idea, hey, we can burn fossil fuels, society would look at those ideas incredulously, and they'd say, why? The characteristics of fossil fuels are just awful. We only use them because we're stuck with them, and we've been using them for decades. But if we had to introduce them today into a world of clean energy, nobody would accept them. So let me compare PV with batteries to our system. The thing I want to emphasize with this comparison is that this assumes you want to use electricity 24 hours a day, not just when the sun is shining. The cost of PV, you have to have a solar field for the first 8 hours, and then you have to have 2 more solar fields of the same size for the next 16 hours when the sun's not shining. Then you have to have batteries for those 16 hours. And the total cost is $9,200 a kilowatt, making these assumptions here. And you still don't have any power when you have cloudy weather. Now you still need a backup. With our system, assuming a total installed cost of $4,500 a kilowatt, we produce power all the time, and we have an inherent backup system. Some of you may or may not know about the market opportunity in CSP, because it's quite enormous. CSP works where the color is closest to red, and the redder it is, the clearer the skies. I have one for Sri Lanka in just a second here. It's not quite that bad. On this map it is. But it turns out that about 40% of the world's population is served within the area that CSP is applicable, within transmission distance. Sri Lanka is blessed with a lot of sun, but it's not blessed with a lot of direct normal insolation, DNI, the kind of clear radiation unhindered by clouds, humidity, pollution. And the best places are known. These places are known. This is one of the very best. And then, of course, on the perimeter down here, there's a spot down here. So you have to, in the case of Sri Lanka, we're able to deploy on rolling terrain. We are the most efficient use of land compared with PV or CSP. And what I mean by that is the number of kilowatt hours per year per acre. So a megawatt of PV requires less land than a megawatt of our system, but our system, remember, produces power all the time, not just when the sun is shining. Scalable and distributed, so we can put one here, we can put one here. I mean, we don't need to build a big gargantuan CSP plant. No water is required. Remember, it's a Brayton system, except to clean the heliostats. We have no environmental issues that we know of. And the technical requirements, because it's a really straightforward, it doesn't require any specialized training to operate. You can see CSP is growing. These are projects that are all over the world that are known. And 6 countries have now established targets for CSP totaling more than 60 gigawatts over the next 20 years. And that does not include the countries that have not established targets, but where CSP is already being deployed anyway. The total is, well, this is RMB. This is from a presentation I made in China, so I'll have to fix that for my lecture at JAFNA tomorrow. This is the amount that's installed, about 5 gigawatts. 2 more under construction, and 3 more gigawatts are planned. And this is the CSP forecast. And of course, there are conservative, middle ground, and optimistic. But as you can see here, we're talking about quite a lot of potential deployment of CSP over the next couple of decades. The status of our commercialization is that we've signed agreements with Masdar Institute and Masdar Corporation to build a reference plant in Abu Dhabi. We're in the process of negotiating a JV with the Tsinghua University Holdings Company. Many of you are familiar with the fact that Tsinghua is one of the finest, actually it's rated the finest university in China. And we've signed an MOU with an Indian partner to build a plant in India. The Ministry of New and Renewable Energy has promised financial support to build that plant, and we've signed an MOU with a Canadian partner to build a reference plant funded by the British Columbian government. We have an MOU with a first customer here in Sri Lanka to build 10 megawatts. We had a number of meetings yesterday with very key, and you know who they are, the key officials here in Sri Lanka, and they're very excited about this technology. And we signed an MOU to build commercial plants in South Africa as well. And while I've been here this week, I got here Monday, I've had email exchanges with 3 other people in 3 other countries totaling over 100 megawatts. And we don't even have data of an operating system. People really, really like this approach. So this is the Sri Lankan opportunity. First of all, as you can see from the design, many of these components are either already being made in Sri Lanka or can readily be made. In fact, more than 50% of the total cost of the system. The tower is an ordinary tower. The thermal storage is made of brick. The heliostats, the glass may not be made here. Saint-Gobain is an example of a supplier, but all of the metal parts can easily be made in Sri Lanka. And then, of course, all the logistics, the construction, the manufacturing of ancillary buildings and whatnot are made here. So the benefits to Sri Lanka ultimately will be a stronger economy. This approach will help secure national energy efficiency by reduced importing of your energy, coal, fossil fuels, petroleum, diesel, this kind of thing. It'll provide reliable, affordable, firmly dispatchable baseload. And what people often don't appreciate is that solar and wind, and of course our system, provide stable, predictable energy costs for decades into the future. Talking with a gentleman last night about your hydro, and the question was, well, how is climate change affecting your hydro resource? And he says, we don't know for sure. It's been dry, but we don't know if that's going to last. And I said, so how can you plan a grid? How can you plan a nation's energy supply if you don't know the future resource of hydro? And he said, you're right. We can do this with clean energy. We can predict the future. Minimize capital investments for power infrastructure. Again, reduce distribution and transmission, and no need for backup power plant if this one fails, because this one won't fail. Stabilizes the grid, minimizes energy imports, improves balance of trade, creates jobs, increases industrial activity. So I don't have a wrap-up thing to say other than, again, thank you for giving me this opportunity to talk. I hope I haven't kept you too long. Let's see. No, it's 6:20. Barely enough time for some 10 minutes of questions, but I sure welcome your questions. Thank you very much.